I'd said I wanted to take a look at another one of these examples, and I guess technically we're revisiting an example we've already done, but you know, you probably are used to me maximizing example mileage at this point. If not, get used to it. It's going to happen again. So we have this rational function that we considered in the continuity section, the cubic, over the quadratic. I have conveniently gone ahead and put the factored version up here, and I wanted to take a look at a sign diagram for this particular function, and then consider some limit behavior type stuff. So based on what we've got here, we have discontinuities at x equals 2 and x equals 3, and we would have zeros for from the top of the thing coming at x equals 0, x equals -1. You might pause for a moment and say, well, is x equals 2 also a 0 because it's down here in the list of points of discontinuity? No. Discontinuity always wins out over the zeros in that instance, so just keep that in mind. So we need tick marks for -1, 0, 2, and 3. And this, is what we call removable discontinuity. You'll notice, we could conveniently sort of escort those out if we were evaluating a limit, so if limit would end up existing at 2. At 3, nothing like that happens. So based on what we've said before, that would be a vertical asymptote on our graph. All right, so now let's make our way through here. So on this side of -1, everything is going to be negative because minus you got all three of those are subtracting something from a number that's already negative, right? So this one here, even if you add 1 to say -2, still a minus. All right, so 1, 2, 3, 4, 5 negatives. That's an odd number, so the entire thing is again negative. Sliding into this segment of our number line, the only thing that's going to change is that guy right there, because again, these are all subtractions of something that's less than 0. This is already less than 0. On the other hand, like -1/2 plus 1, you've bounced it over to the other side, right? So 1, 2, 3, 4 minuses. Yeah, hopefully you kind of get the idea here. Gosh, there we go. Once we go past 0, this one changes sign. So now plus, plus, minus, minus, minus. 3 negatives. 2 of them would cancel each other out, but the whole thing remains negative. Once we go past 2, well, 2.5 minus 2 is now positive. But so is that guy down there. So the sign actually ends up not changing in this instance. And then lastly, once we hop past 3, well, all 5 terms would be positive, so the entire result is in fact positive. Now, if we were wanting to consider some limiting behavior related to this guy, let's take a look at what is going on there. The left-hand limit of our function as we approach 3. So 3 from the left. All right, so that means we got to stay to the left of 3. We can't cross the vertical asymptote like the Gandalf picture. We have to go down that way. So that would be -infinity. So, on the other hand, if we approach from the right, now we're on this side, the right-hand side. We can't go back, well, we can't go across the line, but we also can't drop below the axis. That's all we can do. That is approaching positive infinity. All right, so as part of the sign diagram stuff, I wanted to take a look at one more example real quick. So, because it's easy to slip on something here. So say I wanted the right-hand limit of my function here as x is approaching 2. So I said from the right, I got the superscript there. Now, what will often end up happening when I see students do this is they see this minus sign on the sign diagram, and they say, well, I'm approaching 2, so my limit has to be approaching -infinity. Hopefully you see the problem there. If not, I drew this in specifically because that's where we had a vertical asymptote because of the non-zero numerator, zero denominator thing. We also kind of said previously this x minus 2 term kind of would go away if we were evaluating a limit. This is what we call a removable discontinuity. By definition, that means the limit has to exist, which means it can't be positive or negative infinity. So don't fall for that trap. So we can safely cancel those guys out. For working this thing out, we'd have x times x plus 1 over x minus 3. Again, if you had the x minus 2's written in and cancel them here, that's fine by me. And now we can direct substitute. We'd have 2 times 2 plus 1 is 3, all over 2 minus 3. So I think we should be getting a limiting value of negative 6, which is most definitely not positive or negative infinity. That is a very finite number. So be careful with that every now and again. That's the sort of thing that devious math teachers like to do, is, throw something like that at you, like with the intention of lulling you into, oh, if I have to draw a sign diagram, obviously my answer needs to be positive or negative infinity. Not always. Okay, so let me clear this off, and I wanted to take a look at some of those problems in that notes file I suggested last time, so we can take a look at what's going on as far as vertical asymptotes are concerned. Okay, so when it comes to talking about vertical asymptotes, the big thing to keep in mind is you'll notice most of the examples are all rational functions. So if a rational function like this comes up, yeah, more or less vertical asymptotes occur where you have that zero denominator, non-zero numerator thing going on. So if we take a look at the various examples here, we have 1 over 2 times x plus 4. So what value of x would end up making the denominator of this thing 0? Because the numerator is just 1, so nothing can happen there. That would be x equals negative 4. Be careful on this front. Remember, the vertical asymptote is not just the number. Technically, a vertical asymptote is a line. So, frequently you'll need to write an equation for a line in that instance. So just be careful. So next we've got, we don't have a 1 up top. We have x squared plus 4 over x squared minus 4. So we can factor the bottom. It's a difference of squares. The top, you can't really break that thing apart at all. X squared plus 4 is what you might have heard called an irreducible quadratic at some point in the past. Yeah, you can't really factor that thing if you're not willing to, if you're insistent on sticking with real numbers. So that's as far as I can go, because this thing, no matter what real number you plug in, is always positive, right? The lowest it can get is 4. So each of these is a place where if you feed that in, you get a 0 denominator, non-zero numerator. So we have a pair of vertical asymptotes in that case. All right, then it flips the script, and we have x squared minus 4 over x squared plus 4. So this time around, with the signs reversed, as we said, there are no x values that would make the bottom of this thing be 0. So no matter what, you have something over a non-zero number. There's no weird limiting behavior going on here. So let me be specific here. No vertical asymptotes. All right. So that's next to last guy here. All right. So the very final one, and I should be writing f of x equals for all of these things, but I really am short on board space. So I've got that right there. This time around, we kind of need to dig in and factor things, right? Well, I guess we factored the bottom, I had to write a square when I didn't need it. Okay, so we have x plus 2, x minus 2, yet again, down below. Top side, looking at this guy, if you need a moment to factor it, that's fine. Like I said, hit pause. When I worked this out, I got x plus 4, x minus 2. So if we're looking at this again, remember, the numerator can't give us a vertical asymptote. That's not how these things work. So looking here, x equals negative 2 gives us a vertical asymptote, But x equals positive 2 this time around, note we got those terms. They kind of nix each other. So only x equals negative 2 in this case. All right. So that's looking at vertical asymptotes and limits that end up approaching positive or negative infinity. I've got one last thing I want to take a look at. Just it's something I pretty much always discuss in class, and like I said, I want to show it to you. So give me just a sec here. So this is just kind of a story. So I don't know how authentic it is, but I've heard the story told in a few different places about a teacher who was working with limits and infinity and stuff like that with his students, and he presents this example. So the limit as x approaches 8 of 1 over x minus 8 quantity squared, and he explains why that limit ends up giving him this. So he wanted to test how well his students understood the notion, so he gave them this problem. So subtle variation on a theme, right? So he puts them to work and they kind of scribble for a bit. And he notices a shocking number of his students finish really, really quickly. And so, he ends up, having one of his, more, outspoken students come to the board to present his work on the problem. And this is what he gets back. I'm sorry.